Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light. In my previous lecture, I gave a short biographical introduction to Hermann von Helmholtz, who is an ex-author that we are going to be studying in this course. Mostly in that lecture, I was reading some biographical notes and some context in which he was doing his work. The thing we're going to focus on, once again, is his famous lecture titled On the Conservation of Force. Now, I emphasized last time that I think it's really important that you carefully read this. It's really a wonderful set of lectures, and for me to lecture on his lectures seems a little bit awkward. So there's so much interesting stuff that he brings out in these lectures. I can't encourage you enough to read these. But what I want to do is I want to just highlight some of the things that Helmholtz talks about in these lectures. Maybe I should make one other comment on the title of this. Helmholtz titles this On the Conservation of Force. And you might be a bit perplexed by this. After all, today we call the topic that he's discussing in this lecture the conservation of energy. So why does he call it on the conservation of force? Well, you have to understand that the kind of terminology that is used in physics today was really being developed by the scientists that we're reading in this semester. So you might recall that someone like Hans Christian Ørsted did not talk about magnetic fields per se. He talked about the conflict of electricity flowing around a wire. So these authors were really struggling to come up with words to express the kinds of things that we take for granted today. So similarly, Helmholtz talks about the conservation of force, but he explains what he means by that nature has a limited capacity to bring force into motion. And you'll see in there the concept of what he's going to call work or quantity of work. Work is a force times a distance, which today we relate work to energy, but that terminology was not yet used at Helmholtz's time. So you just have to keep that in mind when you're reading this article. Okay, let's look at page 101, where Helmholtz starts out. And the first thing that he does is he starts talking about the virtues of the natural sciences, about how they've led to great increases in the life of civilized nations. And so he talks a bit about the impact of science on travel and political power and so on. I think that he makes some very interesting comments there. And then the next thing that he does is talk about the distinction between what he calls the physical sciences, I believe, and the mental sciences. And some examples of the physical sciences, I suppose, where is this? On page 101, he talks about the physical sciences as being ones that can be formulated in terms of exact laws that allow for very precise mathematical predictions. And he gives it as an example of that, Newton's universal law of gravity, that you can determine the location of planets, stars, the moon, and so on in the past and future years and centuries to a fraction of a minute. So that's the kind of precision with which one can expect to make predictions in these physical sciences. And then he goes on to mention on the next page, page 102, what he calls the mental sciences, so the study of psychology perhaps, and history and economics. And he mentions that these two obey exact kind of laws. There are laws that societies obey and laws that the human mind obeys, but they're much more difficult to write out in mathematical form. So they're not as susceptible to kind of precise predictive power as the physical sciences are. So those are some interesting comments and observations. You may or may not agree with how he makes this division, but it's an interesting way of thinking about it. He also goes on to say, and here I'm reading from about 2/3 of the way down on page 102, he says, "The last decades of scientific development have led us to the recognition of a new universal law of all natural phenomena, which from its extraordinarily extended range and from the connection which it constitutes between natural phenomena of all kinds, even of the remotest times and the most distant places, is especially fitted to give us an idea of what I have described as the character of the natural sciences, which I've chosen as a subject of this lecture. And this law," he says, "is the law of conservation of force." And again, we would call this the law of conservation of energy. So he's going to be talking specifically about this law as a case of this natural sciences. I think I might have said physical sciences, but I guess he calls them natural sciences as opposed to the mental sciences. He does mention that this is not an entirely new law, that it was articulated in somewhat limited form by earlier thinkers such as Isaac Newton and Daniel Bernoulli and Count Rumford and Humphrey Davy. So for those of you who have read some of Newton's Principia, you might recall that in his scholium in the Principia book 1, I guess it's the scholium on his laws of motion, where he talks about how for every force there's an equal and opposite force, the scholium on the third law of motion. And some of the ideas that are presented in there are touching on this idea of conservation of energy, although it's a very limited form. I'm not sure what he's talking about with the work of Daniel Bernoulli. I know he was a mathematician that did a lot of work on fluid dynamics, he and his brothers, but I suspect that he had some mathematical formulation that was similar to the law of conservation of force. I am familiar with the work of Count Rumford. Rumford was a British loyalist during the American Civil War, lived in the United States, and I think he ended up moving back to England because he was not a fan of the American Revolution. Anyhow, he was doing a lot of work on boring cannons in his shop, so drilling holes in the iron that would make cannons, and he was relating the amount of work that you have to do in drilling the cannon to the temperature rise of the metal of the cannon, which is really an early recognition of the law of conservation of energy, that physical work, forces of friction, can show up as heat energy. And then Humphrey Davy, I guess I can't make too many comments about that, but he also mentions Julius Robert Mayer, a Schwabian physician who did some work on the conservation of energy, and finally James Prescott Joule. And Joule is probably the most famous of these early thinkers on the conservation of energy. You might recognize that the unit of energy is today called the joule, and what Joule did, Helmholtz will be talking about this in this article in some more detail. What Joule did is he rotated a shaft in a liquid bath using some horses carrying this paddle around, and he measured the amount of work that was done on this paddle and then the amount of heat that was generated in this liquid bath. And so he was able to relate the amount of work that you do to amount of temperature rise. And so that was a mathematical approach, or I guess a quantitative approach to the conservation of energy. So Helmholtz mentions all of these folks as precursors to this more general law that he's going to be talking about in this article. But what he has to do, first of all, is he wants to talk about, in order to talk about the conservation of force or conservation of energy, he first has to define a quantity of work. And this is done at the bottom of page 102. He mentions that the law in question asserts that the quantity of force which can be brought into action in the whole of nature is unchangeable. So there's something that cannot change in nature, something the overall quantity of which is limited. And he says that can be neither increased nor diminished. And then he goes on to say, my first object will be to explain to you what is understood by quantity of force, or, as the same idea is more popularly expressed with reference to its technical application, what we call amount of work in the mechanical sense of the word. So he's going to define the amount of work. And this is a technical term. This is still the terminology that's used. So I want to say a few things about this, the amount of work or the quantity of work. He mentions that there's a colloquial sense in which we use the term work, like I have a lot of homework today, or it takes a lot of work to do these math problems, something like that. And that's not the sense in which the word work is used in the technical sense in physics. In physics, the amount of work is related to a force moving over a distance. So he gives some examples to kind of set the stage for this. He mentions on this page 103, the work of different kinds of workers. He says, the external work, I'm reading about the second full paragraph down, the external work of man is of the most varied kinds as regards the force of, or ease, the form and rapidity of the motion used on it, and the kind of work produced. But both the arm of the blacksmith who delivers his powerful blows with a heavy hammer, and that of the violinist who produces the most delicate variations in sound, and the hand of the lace maker who worked with thread so fine that they are on the verge of the invisible, all these acquire the force which moves them in the same manner and by the same organs, namely the muscles of the arms. An arm, the muscles of which are lamed, is incapable of doing any work. The moving force of the muscle must be at work in it, and these must obey the nerves which bring to them orders from the brain. That member is then capable of the greatest variety of motions. It can compel the most varied instruments to execute the most diverse tasks. So he's pointing out there that the human arm is able to apply a force to move an object, whether that object is the bow of a violin, or the needle of a lace maker, or the hammer of a blacksmith. And then he goes on to relate the force moving objects that humans carry out to the force moving objects that machines carry out. He says, just so it is with machines. They are used for the most diversified arrangements. We produce by their agency an infinite variety of movements with the most various degrees of force and rapidity, from powerful steam hammers and rolling mills, where gigantic masses of iron are cut and shaped like butter, to spinning and weaving frames, the work of which rivals that of the spider. modern mechanism has the richest choice of means of transferring the motion of one set of rolling wheels to another with greater or lesser velocity, of changing the rotating motion of wheels into the up and down motion of the piston rod, of the shuttle, of falling hammers and stamps, or conversely of changing the latter into the former, or it can, on the other hand, change the movement of uniform into those of varying velocity, and so forth. And he goes on to say they all need a moving force which sets and keeps them in motion. So it's interesting here, he's drawing this connection between human action, human forces exerting forces over a distance, and machines. This is a way that Helmholtz is thinking about this, okay? And then what he does is he goes on to talk about an example of how to calculate the amount of work that something does. So if you look at the next page, he starts talking about an example of a clock. So let's use this as an example. I'm going to write some things down here. So I'm going to write down calculating the amount of work done by a force. Okay, and I'm just going to write down the answer first, and I'll talk about, so I'll kind of give it away right away. He says the work that is done by a force is equal to the force itself times the distance that it moves. Or if you would like this in shorthand, W equals FD. Okay, so this is, it's the amount of work done. And so if, for example, you apply a force of 10 pounds and you lift an object 1 foot, that would be 10 foot-pounds. So you'd take 10 pounds, a 10-pound force, and you multiply that by 1 foot, the distance moved, and that would be 10 foot-pounds. If you like the imperial system of measurement, if you like the international system of measurement, then you would call it you would use Newton meters, and that would be an amount of work. So how does he arrive at this relationship? He uses the example of a clock. Okay, and specifically, he used the example of, you think about an old grandfather clock. How does one of these clocks work? Well, you have some kind of shaft. This drawing is not going to be great, but you've got some kind of shaft like this. And then hanging over the shaft, I'll make different colors to maybe make it easier to see what's going on. You've got a string that's wrapped around the shaft, okay? And then hanging from this, you've got some weight. And this weight is able to, the weight is able to fall. So this is a falling weight, and when it falls, it turns this shaft, and if you arrange this carefully, you might have some kind of teeth on this, on the outside right here. And then as this turns, if you have some kind of stopper right here that's able to stop the turning, and as this turns, maybe you have a spring of some sort, maybe in here, that pulls this stopper up into one of these grooves, and if it slips, basically, as this thing falls right here, this snaps out of one of these grooves and into another groove, and in so doing, if this stopper is attached to a shaft like this, with a weight on it, then you can have this thing experience a kick. It swings this way every time that the weight falls through one of these teeth. And then it slides, and then it swings back, and then the weight falls another tooth, and it swings the other way. And so this falling weight produces a swinging pendulum. And so long as this weight keeps falling, it keeps kicking the pendulum and making it swing. And you might imagine that you could have some gears hooked up to this somehow that turn the dials or the hands of a clock or something like that. If you do this very careful mechanical arrangement, you might have the hands of a clock that this reads, okay? So that's the basic idea of one of these grandfather clocks. I know this is an oversimplification, but that's the idea. Okay, and the point that he makes is you can get work out of this and make this pendulum swing, provided there's this weight moving over some distance. There's some distance through which this falls. You got oops, this is a weight. Don't confuse this with work. Maybe this weight is, if the weight is equal to, let's say, a 1 pound weight. And if it falls a distance, let's say a distance is 1 foot, then you multiply these together, you get a work of 1 foot-pound. Why is multiplying these together relevant? Like, why is this a relevant quantity? Well, he mentions that if you have, instead of just a 1 pound weight hanging from a clock falling 1 foot, you have 10 1 pound weights driving 10 clocks. It does 10 times as much clock work. So by increasing the amount of weight that is falling through this 1 foot distance, you're proportionally increasing the amount of work that can be done. And similarly, if you just had one clock and you had a 1 pound weight falling, instead of through 1 foot, you have it falling through 5 feet, then you would have 5 foot-pounds of work. The clock could do 5 times as much work. That is, it could run for 5 times as long. So by increasing the weight or by increasing the distance, in both ways you can increase the amount of work that is done by this clock, the amount of time it keeps going. Now it's also important to note, as he mentions, that once this weight hits the floor, this weight, it still has weight. It's not like the 1 pound has gone away, but this clock is exhausted. It's no longer able to do any work unless you lift the weight back up through that distance. And in so doing, you have to do work in lifting this weight. But then once you've done that work in lifting the weight back up, then you can reset the clock, and then the clock can run again. Okay? So there's this quantity of work is something that is a very significant feature of nature. And so what he did in this first few pages is he defined what he means by work, and then in the subsequent pages he's going to explain different applications. So why don't we stop there, and we'll pick this up next time.